All right, here we go. Have another day for you on definite integrals. Today we're going to be talking about different properties of definite integrals. So what it means to add them together, to multiply by a constant, to do them backwards, just things that will make sense once you've seen them, but you do need to sort of see them once. We're going to explain these properties basically every time in two ways. Once, using the interpretation of the area under the curve, so sort of like geometry and shading, and a second time using the fundamental theorem of calculus. So as a reminder, the fundamental theorem of calculus says if you have some function, f of x, so I'll doodle one here, and I wanted to know the area under the curve from some point A to some point B, this is the definite integral. That's what this represents. This right here means exactly that, the area between f of x and the x-axis from A to B. The fundamental theorem of calculus links this idea to the idea of a derivative and antiderivative by saying that you can also calculate this by taking the antiderivative of f. So doing the reverse power rule or whatever you may need to do, taking the antiderivative and plugging in b, subtracting the antiderivative and plugging in a. And that is the fundamental theorem of calculus in a nutshell. And we're going to see how it can be used to justify a lot of these properties of the fundamental theorem. So let's go through them. Property number one, if A and B, so if the start, right, this is going to be the start, and the finish are the same number, right? This is probably the easiest one to interpret. Well, then you're just doing f of a, capital F of a, minus capital F of a, anything minus itself, is 0. And geometrically, that should also make sense, right? If I say, what is the area under this curve from 4 to 4? Well, it doesn't have any width, so it can't have any area. So if you have a definite integral from a number to itself with a distance of 0, that definite integral is 0. So property number one, out of the way, right? That's a pretty straightforward one. The next one that I think is also sort of geometrically very straightforward, let's imagine that we have three numbers, and let's say we go from 2 to 6. Let's say A is 2, B is 4, and C is 6. What this property here says is, if I find the definite integral from A to B, so I find the area under the curve from A to B, and I add to that the definite integral from B to C, well, that is equal to the definite integral of both of these things. And so maybe I'll draw this sort of like squiggly left and right. And so basically what this is saying, if you have one integral that starts where another one ends, so there can't be any gap here, right? So notice what's really important is that B is the end of the first integral and the start of the second one. So there's no overlap here. Well, then you can take the distance from the first starting point A to the second ending point C. Right, so geometrically this makes sense. Those areas should be equal to each other. So here's from this one on Desmos. The definite integral from 2 to 4 is 6.17. The definite integral from 4 to 6 is 8.58. And if you combine those two things together, 14.75 would be those two areas added together. Again, super important. The end of the first one, right, the B's have to be the same. The B's in that have to be exactly the same. So that's property number 2. Property number 3 is an interesting one. If your definite integral is set up, I'm going to use air quotes here, correctly, meaning that A is on the left and B is on the right, right? If A is less than B, so we go from 4 to 8 here, remember I said that if you are above the x-axis, then your area here is positive. If it was below the x-axis, it would be negative. However, it is not an ironclad rule that these have to go left to right. So if we go from B to A, basically this works backwards. So if you're going from right to left, so if we go from right to left, well, yes, that's above the x-axis, but we're doing it backwards, so our second integral would be negative here. So notice on the Desmos, if I go from 4 to 8, what you would imagine is, the natural left to right way, I have a positive area. If I go right to left, maybe I'll do this one in red. If I go right to left, I'll have a negative area. Now, the same thing would be true, but I didn't do an example of this, but the same thing would be true in reverse if your function went below the axis. So in this case, if you were finding this area here from A to B, the definite integral from A to B of this second function that I did, well, from A to B, this is below the axis, so that would be less than 0. But if I went backwards from B to A, that definite integral, okay, it's under, so it's negative, but then my start and finish are backwards, so that would be positive. So you just have to keep that in mind as you're doing that. All right, 3 down, property number 3 done. The next ones are just so quick that we're just going to kind of go through them in about 3 seconds. First is that just like with derivatives, remember if I took the derivative of like 3 sine of x, remember that this is the same thing as just pulling that 3 out, 3 times the derivative of the sine of x. The same property applies here. If you have a constant number, you can pull it out front. And it has to, because integration and the derivative are the inverse of each other. So you can pull those constants outside first. The second one is, again, similarly here. Remember, if we had the derivative of some function f, I'm just doing shorthand here, no of x. Remember, this is the same thing as taking the derivative of the first function and adding to the derivative of the second function. Same idea applies here. If you have the definite integral of 2 functions being added together, well, you can separate those out into 2 separate definite integrals, and we'll see why that might be useful in a second. So let's go ahead and let's run through first some quick examples, 2 toughies, and then that'll be it for today. So here are some quick examples, and a common way that the AP Calculus exam tests your ability to apply these properties is they won't give you a function. They'll just give you some definite integrals and state what their values are. So we're told that the definite integral from 0 to 3 of f of x is 6. Okay, well then 3 to 0, I've just done that swap, right? These have gone backwards. Instead of going left to right, we're going right to left. So I'd use the negative property, or like that B to A property. This would be -6. All right, next one, 0 to 7. Well, from 0 to 7 is the same thing as from 0 to 3 plus from 3 to 7, right? Those are the same thing by the second property that we did. The 3's match up, right? The start of one matches the finish of the other, so we can just add these up, 6 plus -8. Again, just sourcing those from what we were given. This would be -2. This one, super straightforward. There's no distance here. We haven't gone anywhere. That definite integral is 0. Okay, next one, a couple things going on. So first, I'm just going to pull out that 3. So this is equal to 3 times the definite integral from 7 to 3 of f of x. And if I'm being really formal here, I can say, okay, well, 3 to 7 is backwards from what I had. So this is -3. Notice I pulled that negative sign out, right? I'm pulling that negative sign out, and then I'm going to flip these, right? I'm just being super formal here about showing each step. So this would be -3 times -8 to be +24. So first I pulled out the 3, then I put it back in the correct order by adding a negative sign, and then finally I pulled the -8 that I knew was the definite integral from 3 to 7, multiplied by -3 to get 24. Last quick example before a couple toughies. If we have, and this is a very common format and it really trips people up, if we have 2 separate integrals here, I'm going to write this because it makes more sense once you've separated it. 2 separate integrals from 3 to 7 of the number 2. Don't forget, you can take the integral of the number 2, because what's the number 2? Well, the number 2 is just a straight line at y equals 2. And so the integral from 3 to 7, right, this area under the curve, well, should just be 2 times 4. It should just be 8, but we'll do the antiderivative just to show it. But if you can think about it geometrically, sometimes you can do those pretty quickly. And we're going to add that to, I'm going to do 2 steps here, pull that 3 out. 3 times the definite integral from 3 to 7 of f of x. Well, this we already know, right? This we know is -8. This is 3, so this is going to be minus 24 when this is all said and done here. 3 times -8. But what's going on here, right? If you didn't think of the geometric interpretation, well, the antiderivative of 2 is 2x, and we're going to evaluate it from 7 to 3. So this is using the fundamental theorem of calculus. So we're going to evaluate this from 7 to 3. So we're going to have 2 times 7 is 14, minus 2 times 3 is 6, all of that minus 24. And so what this would end up being is 8 minus 24. You'd get here -16. So a few different things going on there on that one. Just to recap here, again, I do think this is just like an interesting point to kind of connect these things. Notice what I did here, right? That is applying the fundamental theorem of calculus. This right here, that is capital F of B minus capital F of A. But if you didn't catch it the first time, just remember, the definite integral is the area under the curve. The area under what curve? The line y equals 2. So the area under the line y equals 2 from 3 to 7 is 4 times 2 is 8. So you get the same thing either way, and that would always work. We finish the rest of that to get -16. All right, last 2 examples today. Going to do 2 that are sort of at the level of delta math, which they're kind of like puzzle pieces that you have to figure out. Okay, how do I put together one piece of information that I know and 2 pieces of information that I know to get the answer? And you're going to need to use properties, and you're probably going to need to use the FTC sometimes. So what we're trying to figure out is the definite integral from 1 to 6 of 2 times f of x. And so let me look at what I have. Well, this I could rewrite this. The first thing I'm going to do, this is 2 times the definite integral from 1 to 6 of f of x. I'm going to pull that 2 out. Then I need to think, okay, I don't have anything that's 1 to 6, but what do I have? I have something that's from -1 to 1, and I have something that's from -1 to 6. And so this is going to seem a little bit strange here, but what I can do, right, if you really just sort of think about what's happening here, if I take the definite integral from -1 to 6 of f of x, right, the area under the curve from -1 to 6, and I subtract the area under the curve from -1 to 1 of this function, well, that's going to be equal to the area from 1 to 6, right? If you think about this as sort of like overlapping regions here, and I guess I need to go to -1, if I have some function here and I find the area from -1 to 6, I find this whole area, and then I subtract away the chunk from -1 to 1, I subtract that away, well, what am I left with? I'm left with the area from 1 to 6. And so now it's just a matter of plugging these elements in. So -1 to 6, we're told is the area under the curve is 16. -1 to 1, ooh, sneaky, these are backwards, right? I didn't really see this the first time. These are backwards. So I'm going to change this to a plus sign because I wrote it as -1 to 1, but really it was 1 to -1. So that was a tricky one there. This is going to be 16 plus -6, and that's going to be equal to the definite integral from 1 to 6 of f of x. And so this is going to be 10 is equal to this thing. But remember, what we were actually asked to find is twice that. So the final answer here would be twice that. The final answer there would be 20, okay? All right, let's do one more here, and I'll try and do that one a little bit more cleanly here. All right, we're trying to find the definite integral from -9 to -2 of f of x plus 1. Well, the first thing I see here is I'm going to have to split this up. This is the definite integral from -9 to -2 of f of x plus the definite integral from -9 to -2 of 1. Okay, so at least these are in the correct order here. So let's see. This I know I can do using the FTC or thinking about sort of geometry there. But this one the one on the left I'm gonna need help with. So how do I get from -9 to -2? Well, I see my -9 here, but it's flipped. So the first thing I'm gonna do is I'm gonna rewrite this one as from -9 to 3 of f of x dx. Well, it's the opposite. It's 11. Okay, cool. So I've got that. And then I've got one that goes from -2 to 3. Okay, so once again, just sort of like thinking about this geometrically, if I've got some function, right now, I know what the area under the curve is from -9 to 3. So I make up a curve here. Right now, I know this area from -9 to 3. But I only want, remember, I only wanted -9 to -2. So once again, I need to do that subtraction method. I need to subtract the area from -2 to +3. So what we're going to do here is we are going to write out the definite integral from -9 to 3 of f of x minus the definite integral from -2 to 3 of f of x. This will be equal to, and I got lucky, it all kind of lined up here. This will be equal to the definite integral from -9 to -2. This we just found is 11 instead of -11 because it was given to us backwards. This we are told is 2, and so we now know that this here equals 9. Now that's still, we have to figure out what this is, which you can either think about geometrically, okay? It is the line y equals 1 drawn from -9. Oh, I did that kind of backwards in terms of the ratios there, so let me redo that. If you've got your function here, draw that clean. If we're going from -9 to 2 under the line y equals 1, well, that's 9 plus 2, that's going to be 11. But just to make sure we see this another way, using the FTC, this is going to be equal to the antiderivative of 1 is 1x from -9 to -2. And so what you're going to have here is you're going to have plugged in here from -9. Oh, it's to -2, not to +2. I was like, wait, that's 7. What happened here? So this is only going to be to -2, not to +2. And so this area here would be 7. And so we're going to have -2 minus -9. That's going to get us 7. So altogether, we're going to have 9 plus 7. We're going to have here, well, this is equal to 9. And then we're going to add 2 plus 7 to get final answer of 16.